life on Earth may be mathematically implausible. That's the provocative claim behind a recent study suggesting that the very first living cell was far too complex to appear by chance in Earth's early chemistry. If the math is right, our existence seems to defy probability itself. But before jumping to conclusions about miracles or extraterrestrials, let's unpack what this study actually says, how it fits into decades of research, and what it means for the search for life elsewhere in the universe. In July 2025, Robert G. Andrews of Imperial College London published a preprint titled The Unreasonable Likelihood of Being, Origin of Life, Terraforming, and AI. His approach was unusual. Instead of proposing a specific chemical pathway for life's origin, he applied the tools of information theory and algorithmic complexity. In essence, he asked how likely it would be for the enormous amount of structured information inside even the simplest protocell to emerge spontaneously from random molecular shuffling. The conclusion was stark. If you model prebiotic chemistry as a system that simply explores possibilities at random, the odds of stumbling across a functional, self-replicating cell in the short geological window available on early Earth appear astronomically small. To illustrate, imagine trying to type out Shakespeare's Hamlet by randomly pressing keys. The search space, the total number of possible strings, is vast, and the fraction that actually produce a coherent play is vanishingly tiny. That is how the problem of abiogenesis looks, if you assume chemistry is nothing more than blind randomness. The analogy is imperfect, but it conveys why Andres and others see a deep mathematical barrier to life arising purely by chance. But here's the catch. Chemistry is not random dice rolling. Real molecules follow rules, and chemical networks are biased in specific ways. Certain monomers are far more common than others. Some reactions are catalyzed by mineral surfaces, and environmental cycles like wetting and drying or exposure to heat and radiation prune unproductive reactions while amplifying others. The real debate is not whether chemistry is biased, it clearly is, but whether those biases are strong enough to funnel matter towards self-replicating, information-rich systems in the time available. This is where thermodynamics comes in. The second law tells us that closed systems tend toward disorder, but Earth has never been a closed system. From the very beginning, sunlight, geothermal heat, and chemical redox gradients poured energy into the planet. Driven by these energy flows, non-equilibrium systems can spontaneously self-organize into so-called dissipative structures. Think of convection cells in a heated fluid or chemical oscillators like the Belousov-Zhabotinsky reaction. Order can emerge, but the question is whether Earth's primordial environments, tidal pools, volcanic vents, mineral-rich clays, could produce not just patterns, but information-rich replicators capable of evolving. Chronology provides a key clue. If life took billions of years to appear, perhaps Andres is right that the barriers are immense. But the evidence points in the opposite direction. Geological records suggest that life may have arisen almost as soon as Earth became habitable. Isotopic signatures hint at biogenic activity as early as 4.1 to 4.2 billion years ago. Stromatolite fossils appear by 3.7 billion years ago, and Bayesian analyses of these timelines, such as a recent study by David Kipping, show that life's early emergence strongly favors the hypothesis that abiogenesis is a rapid process given Earth-like conditions. Statistically, the odds lean more than 10 to 1 in favor of life being fast to appear once the environment stabilizes. That challenges the notion that life is nearly impossible. So how can we reconcile the life is too hard math with the life started quickly data? The answer lies in competing origin of life models. In the RNA World hypothesis, self-replicating ribozymes and lipid vesicles bootstrap early evolution. Biases in prebiotic chemistry, like selective polymerization on mineral surfaces or amplification by wet-dry cycles, shrink the search space dramatically. In metabolism-first theories, networks of mutually catalytic reactions arise naturally from geochemical conditions, bypassing the need for complex genomes at the start. Hydrothermal vent models point to natural proton gradients across mineral membranes that prefigure modern bioenergetics. Each of these scenarios introduces natural pathways for selection and self-organization long before anything resembling a modern cell. Still, Andres raises a valuable point. If you strip away those organizing mechanisms, the math really does look hopeless. That's why his paper functions best as a null model. It tells us what we need: sources of bias, ratcheting mechanisms, and environmental constraints that make life probable rather than miraculous. Without them, the odds are absurdly small. With them, the puzzle becomes more tractable, and the rapid appearance of life on Earth becomes easier to explain. Of course, there are other possibilities. Some scientists and philosophers have suggested panspermia, the idea that life's building blocks, or even primitive cells, arrived on Earth from elsewhere in the cosmos. Natural panspermia could involve microbes hitching a ride on meteorites or comet dust. A more speculative version, directed panspermia, proposes that advanced civilizations deliberately seeded planets like ours. These hypotheses are difficult to test and don't solve the problem of where life began. They simply move it to another world. Unless we find independent evidence for life beyond Earth, such as biosignatures on Mars, Enceladus, or exoplanets, panspermia remains intriguing but unproven. So where does this leave us? The tension between the math says no and the rocks say yes is not a contradiction, but a roadmap. It tells us that chance alone cannot explain life. Something else, geochemistry, physics, energy fluxes, or principles we haven't yet discovered, must have done the heavy lifting. The challenge for the next generation of origin-of-life research is to uncover those mechanisms. That means building long-term laboratory experiments that mimic hydrothermal vents and tidal pools, using microfluidic systems to track chemical evolution over months and years, and deploying AI to search vast chemical networks for emergent autocatalytic sets. It also means refining our planetary timeline, dating microfossils more precisely, constraining the age of the last universal common ancestor, and hunting for biosignatures in ancient rocks and on other worlds. Does the math say life shouldn't exist? Only if we imagine a universe without structure, bias, or feedback. The evidence so far suggests the opposite, that once Earth-like conditions appear, chemistry is guided into pathways that make life not a miracle, but a tendency of the cosmos. Still, until we demonstrate that process in the lab or discover life beyond Earth, the origin of life remains one of science's greatest unsolved mysteries. So what do you think? Was life inevitable, written into the laws of physics and chemistry? Or are we the ultimate cosmic lottery winners, improbably lucky in an otherwise lifeless universe?